Hi, so on this lecture I will be speaking about Fabry Perot instruments, and I will be speaking about these instruments more broadly, and I will basically try to distinguish them between interferometers and etalon type of a Fabry Perot instruments, and further I will define parameters or introduce parameters that can be used to quantify the performance of these kind of instrumentation. So essentially how essentially these kind of resonators they behave, and how we could quantify with a few parameters how well they behave. So this is what I will be speaking about, and essentially this is extending mostly our previous lecture on multiple beam interference. So essentially thin film structures where the thin films are associated with high reflection coefficients, because then we are essentially getting a Fabry Perot interferometer out. And these instruments, the Fabry Perot instruments, broadly speaking, it's based, or they are instruments where we have interference between several different waves or rays, and then this is the kind of like defining quantity of a Fabry Perot instrument. And please recall of the figure that we used in the earlier lecture for a thin film structure. So there essentially we were calculating what were the transmitted irradiances and the reflected irradiances, and there we noticed that indeed we had to take into account many rays playing a part in the total irradiance distribution. So essentially that's an example of a Fabry Perot instrument. So many rays are being reflected and then subsequently give rise to the interference pattern formation. So that's the kind of, broadly speaking, the kind of instruments we are dealing with here. And of course we can generalize readily in the other kind of instruments, Fabry Perot instruments. The interesting thing here is mostly the transmittance function T of these devices. And as we learned in the previous lecture, that depends sensitively on the Airy function, so the calligraphic A letter. So T, the transmittance of a device, it's defined in the same way as the transmittance of an interface. So essentially it's the ratio of the transmitted irradiance, IT, divided with the irradiance of my incident ray, so I naught. And this, in the previous lecture, we learned that this is in fact the Airy function, so A, and this was of course of a form that we have 1 over 1 plus f, the finesse coefficient times sine squared of a delta over 2. And here the delta is the phase difference term associated with my interferometer or instrument here. And f was of a form that it's the square of 2r divided by 1r squared, and r is the reflection coefficient of my cavity. So in the previous example, that was the reflection coefficient of my thin film structure, but equally well I could apply this math into a scenario where I would have 2 mirrors, and then I would be trapping my laser beam between the 2 mirrors. And then if the 2 mirrors would be identical, then this small r here would be actually the reflection coefficient associated with the mirrors. So here, of course, the transmittance depends on the phase difference delta and depends on the finesse coefficient, so capital F, which furthermore depends on the reflection coefficient. And looking at the figure, especially the phase difference and its implicit dependence on different parameters, we see that this transmittance of my resonator, my instrument, depends, well, first of all, it depends on the incident wavelength, lambda null, depends on the refractive index of my intermediate medium, in the case of the thin film structures, on the refractive index of the thin film structure, NT, and then of course of the thickness of the medium, so that would be the thickness or length of my cavity, D. In the case of a thin film structure, that would be the thickness of the thin film, and then of course on the refraction angle theta T, and of course that changes when we are changing the angle of incidence theta I. So what this means, so that there's such a complicated difference or dependence on parameters, so that many things can in principle be measured, or maybe a better word here would be monitored. So for example, etalons, which I'll be introducing shortly, can be used to lock a laser into a specific wavelength of interest. So in that way, for example, we are thinking of a monitoring of my device. So I'm basically trying to keep my laser locked into a very specific wavelength by just using this kind of Fabry-Perot instrumentation. And then there will be some drift in the lasing wavelength due to, for example, some thermal drift in my laser, and that might affect my actual measurements, and I do not want them to be affected. And subsequently, for example, with a Fabry-Perot instrument such as an Etalon, I would be able to monitor the output wavelength of my laser source, and if there would be a drift, I would be able to compensate that by adjusting the laser parameters to really keep the laser wavelength where it should be. And this I can do quite cheaply and quite accurately by using these kind of Fabry-Perot instruments. Basically simple many times as just using an Etalon structure. So this FP instrumentation, Fabry-Perot instrumentation, can be divided into two different classes. So first of all, there are interferometers, where we could think that we are basically adjusting the term of NT times D. Or more importantly, we're adjusting the D, the separation between the two cavity mirrors. As in the figure here, we are adjusting D, possibly here, and then we are actually measuring things as a function of D, and then we're actually measuring something of an interference pattern. Another possibility would be that we would be not modifying the D parameter here. We would be keeping the two mirrors in same location. And we, for example, would have a gaseous substance here. And then we would be modifying the refractive index of my gas. So essentially the NT here. And then I would be seeing an interference pattern being formed as a function of changing refractive index. So that would be another possibility, and this basically is highlighting how a Fabry-Perot interferometer works. So there, the kind of governing principle is that we are adjusting the length of my cavity, D, and then we are measuring the subsequent changes in the interference pattern. Another possibility to consider is that we have an Etalon structure, where one way of thinking is that we are adjusting the angle theta t in the math, and subsequently we are adjusting the kind of irradiance distribution of my outcoming field here. And Etalon structures, please remember, it's exactly like a thin film structure. So we need that we have a high reflection coefficient for these two different interfaces in the Etalon. And here the crucial point, the crucial difference between Etalon and a Fabry-Perot interferometer is that, needless to say, that it's pretty hard to try to change the thickness of my Etalon structure if it's just a single block of a material, so that this cannot be squeezed that much, or it cannot be expanded that much, but rather the changes will be tiny, minuscule, if any. Of course, in practice, like every materials, when we heat them up or we cool them down, their length will be changing, but we cannot as easily control that as a D parameter when we would be really having two mirrors, and then we could, for example, adjust the mirror separation with piezo motors. So this is basically the difference between the interferometers and Etalon structures, so that either we change actively the cavity length or we do not change the cavity length. Either which, they have their pros and cons, and of course with the Etalons they're super simple and they're quite stable, so they do have their moments of goodness when we are thinking about applications. And I didn't remember that you mentioned about this P figure here. So essentially that's showing us what kind of interference profile we would be now measuring when we would have a camera here after the Etalon structure and a lens, so that this is where we would have then the interference patterns forming, for example. Now let's look more carefully into the actual line shapes for the irradiance distributions that we get out as a function of phase difference delta. And on the y-axis, we have something that essentially is proportional to the irradiance or to the Airy function, since we are really now interested in the transmittance t that was essentially equal to the Airy function a. And we want to understand how both Fabry-Perot instruments or both types of Fabry-Perot instruments work out. And in both of the cases, we really must look more carefully into the transmittance function, so the capital T, and how the peaks will shift when we change the phase difference delta. So essentially, we need to look how and what are the parameters that define the transmittance peak positions and their widths. And many times, in terms of applications, it's really the width of the peak that is a key parameter here. So let's define some quantity that we can use to define what is the width of the peak. So let's define a so-called half width value, gamma, or full width at half maximum value that defines that how narrow of a peak I have. So essentially, like I can define a half width value gamma where the peak has been reduced in strength to 1/2 of its original starting point value. So mathematically, essentially, I can state that I can define this half width value gamma by just looking at the locations where the error function gets a value of 1/2. And hence the name, that's why it's called a full width at half maximum value. So now we have coefficients and equations that we have the sine squared of my phase difference delta over 2, and this is 1 over f essentially. So I get 1 over 2 rid of in the original sine squared term. And of course I can write this as a function of the sine. So this is essentially now the square root of fineness coefficient and the inverse of that. So this is how I can simplify things. So essentially I'm taking the square root of both sides, and this is what I'm left. And now I can look at this, that if the fineness coefficient f, capital F, is large, we see that already a small phase difference delta results in a condition that the error function a equals 1 over 2. So essentially, when the sine, and we are now adjusting the phase difference delta here, when that is a value of m pi plus minus delta over 2, when this is this fineness coefficient is large, essentially like we can approximate that this sine is essentially just the phase difference in itself. So we are just like looking at the location where we are close to a value of pi, an integer of pi, and when we are close to that value, then the argument of sine is approximately just this value here. So we can just look at this and verify that by just using power series approximation and verify this. And this is fine as long as we are having a high fineness coefficient, so that this is indeed the case where we are operating. And now from here, we can solve this gamma value, or the full width at half maximum value, that it's essentially 4 divided by square root of fineness coefficient f. So essentially, we're looking at this guy when the error function gets a value of 1 over 2, and we got this relation from here, and now we are just simplifying things. So this was what we place in here, and then we see that we can actually solve for the gamma. And now we see that the reflection coefficient either associated with the cavity mirrors, or in the case of an etalon, the reflection coefficients of the thin film structure, they dictate how large or how narrow is the peak width. And then another way of looking at things is that instead of looking at the fineness coefficient, we can look at something called a fineness of the cavity. So essentially, we can look at the relative width of my transmittance peak. And how we can estimate what is this kind of quantity is that we can look at the subsequent adjacent peaks. So essentially, the distances between the peaks associated with an integer m something and m plus 1. And then we are looking at the kind of relative difference or distance between these two different peaks. And we know that in these cases, the phase difference is an equal of 2 pi, since they are the adjacent peaks. And we know how they are formed, so that they are formed when the phase difference is an integer of 2 pi. So we can actually compare these values to the full width value of a gamma. And now we can calculate this ratio of these two values, and we can define that this is the fineness of my cavity. So like a strange looking f now, this is not just a capital F, but the calligraphic F. And this is defined as 2 pi. So this is the phase difference caused between the adjacent peaks, divided with the gamma term. So this would be the full width at half maximum. And this is the fineness of my cavity. And then we can write this using the fineness coefficient capital F and this is looking like this. And this is another parameter that would tell us right away if it's a large value, how good my cavity actually is. So essentially how narrow peaks I would be able to measure with my cavity. And this really tells something about the performance of the cavity. And it's quite nice because then we would have a single number that we could relate with our instrumentation, and we would be able to kind of understand how good of a device we possibly may have at our hands and disposal. And please note, this does not depend on the length of the cavity, but rather it only depends on the losses. So there's nothing in there in the finesse coefficient here that is related to the length of my cavity. So this is really a relative performance term here, so that when we have a larger cavity, then this is not being modified, but what we should modify to increase the finesse is that we should really modify the reflection coefficients. And if you want to adjust the reflection coefficients, make them closer to unity, then essentially it just means that we are reducing the losses associated with my cavity. So that's the physics playing here. And finally, some examples, some rules of thumb. If we have a typical etalon structure and we are looking at the finesse values, then the calligraphic F is of the order of 10. So this is something that we could do with the usual thin film structures. But if we have a typical interferometer structure, so with that we have two highly reflecting mirrors, then the finesse values can easily range 100,000 and even exceed that. So this is somehow like a kind of telling us a little bit about the difference in performance when we have these two different configurations. Like etalon structures, which are super simple and quite easy to use and can be used to do lots of neat things. And then we have these really Fabry Perot interferometers based on having two mirrors of high reflectivity. And then we can really see that they actually are associated with peaks that are super narrow compared to the usual peak distribution of etalon structures. So this is what I wanted to say in this lecture. I hope that you got something out of it. And next, I will be speaking even further about Fabry Perot structures in terms of spectroscopy, but more of that, of course, in the next lecture. Thanks for listening and enjoy your day. Bye.